Hey, it's Nathan. I'm going to talk about a handful of things today. As always, they're separated out into the sections at these time codes. So if you want to skip to any particular section, you can just scroll along to that particular timestamp or click the chapter links in the description below. So topology textbooks like this one often introduce topologies and topological spaces. And then there's some time spent on examples of topological spaces and some core ideas like that of what a base or basis of a topology is. But then, as you would expect, some of the more fundamental topological operations are introduced, those being the closure and interior operations. So if you're not super familiar with what the closure and interior do, that's okay. You're not going to need a lot of that knowledge to continue with this video. If anything, this video will introduce you to some of the things that you can do with those operations and the facts that you'll need to understand the proof at the end of the video will be given as fact throughout the video as we come across them. For the sake of completeness, though, I'm going to go ahead and put up the definitions for the closure and interior on the board here. Intuitively, a closure of a set is just a way to make a set that you're given, any set at all, into a closed set with respect to some topology. And then similarly, the interior operation is a way to take any set you're given, any one at all, and make it into an open set with respect to a given topology. So the first notable thing about both the closure and interior is that both of these operations are idempotent, which is just fancy math speak for if you do them once, if you do them again, you'll just get the same thing as if you did them once. So for example, if you went ahead and took the closure and you applied the closure twice to some set, you would just get the set that you would get if you just applied the closure once. The other thing that's notable about the interior and closure operations, just from the definition, is that the interior operation can actually be written as a composition of closure and complement operations. So by De Morgan's laws, we end up getting this expression for the interior, which is just a composition of the complement with the closure with the complement. And so you might think that since the structure of each of the individual operations isn't too complicated, there wouldn't be much to say about how these operations create different sets in a topological space. That is, until you go ahead and read some of the exercises that come up. In particular, one of the homework problems that you may encounter from Muncri's topology in particular and other topological textbooks is a hard exercise that's labeled with the name Kuratowski. It asks for a given topological space, show that starting with a given set A, one can form no more than 14 distinct sets by applying the closure and complement operations in any order that you would wish. And 2, for the real numbers in its usual topology, which means exactly what you think it would mean. It's the standard way we think about real numbers and distance between numbers, where you just take the absolute value of the distance between two of them and think about the real numbers in that way. There's a subset for which the maximum of 14 is obtained. This problem is essentially just asking you to prove Kuratowski's 14-set theorem with just a little bit more information than what Kuratowski had when he went ahead and proved it as a part of his PhD thesis, where he also describes how you could go ahead and define topology in terms of a defined closure operation on a set, instead of the way that it's usually taught today, where we define a collection of open sets. An updated version of Kuratowski's PhD thesis was published again in 1922, and since then, the portion of it about the 14-set theorem has become a homework problem for aspiring mathematicians instead of something that's stated as fact with proof in a textbook. So this problem is often labeled as a difficult problem in topology textbooks, and rightfully so. It is a hard problem if you don't know the trick of how to think about what's going on. And it would be a lot harder if you were using a textbook where they don't mention that 14 is a pretty important number in this process. The reason that it's hard, even with 14 being given, is that finding out that the maximum number of possible sets that can be created under closure and complements is 14 doesn't actually tell you that there exists a set that achieves 14 distinct possibilities under these operations, or that you could construct one even. The other thing that's interesting about this problem is that 14 just comes out of nowhere. And so there seems to be some like number theoretic intrigue into why 14 would be the number to do the thing for us with this problem, especially if you're not given that 14 is important, like we're assuming in this video. And then also, aside from just 14 being a weird number to have significance in topology, is that, well, since the interior operation can be expressed as a composition of complement and closure operations, these 14 different possibilities of compositions that you're looking for could be thought of as the family of all possible types of interior and closure-like operations on a given topological space. That is, if the topology realizes 14 different operations. So, why does this work? Well, at this point, if you want to think about the problem for yourself, you should probably go ahead and pause here. I'll give you around like 5 seconds to do so. Otherwise, I'm going to go ahead and jump into the explanation of why this works, and we're just going to go to the board. So while going through this, I'm going to think about the operations that we're working with in a global way. So I'm not going to think about a particular topology or a particular set that we're operating on while we go through this. That is, until we get to the example of a set that realizes all 14 possibilities in the real numbers. But before we get there, it's going to be helpful to build up some language and notation around this global thought of these operations instead of thinking of them operating on a set by themselves. So first off, since the strings of these operations are going to get quite long, I'm going to use a symbolic notation on an alphabet of C and bar, for C being complement and bar being closure, respectively. So for example, the string for the interior operation would be C bar C. And so C bar C of A is the same as taking the complement, then the closure, and then the complement again. Now I need to throw some of those facts that I mentioned earlier at you. Each of these things would be a good exercise to prove if you want to get more familiar with how closure, complements, and interiors interact with each other. So here are some facts. The closure of a set always contains the set that you started with. The interior of a set is always contained by the set that you started with. The closure and interior operations are what we call isotomic operations, which is just a fancy math word for saying that if you have two sets, one contained in the other, then the closure and interior operations respect that containment. So if A is a subset of B, then the closure of A will be a subset of the closure of B. If a set is contained in another set, the complement flips that containment. So if A is a subset of B, then A complement is a superset of B complement. These facts let us define a way to order and manipulate the order of the strings of compositions of the closure and complement operations. That is, if O1 and O2 are operations that are created by composing the complement and closure operations, and for every set A in our space, we have that O1 of A is contained in O2 of A, then we say that O1 is less than or equal to O2. Also, using this convention of less than or equal to, we can go ahead and rewrite that list of facts that we had in terms of the less than or equal to notation for operations. It's also important for us to note that under this convention of less than or equal to, we have that O1 less than or equal to O2 and O2 less than or equal to O1 implies that the operation maps all of our sets in our space to the same sets. So O1 and O2 would be the same operation. So now that we have some notation behind this less than or equal to sign with respect to closure and complement operations, we can go ahead and start thinking about Kuratowski's 14 set problem in a different way. So when we go ahead and look at the first statement, it's just asking us to look at the finite strings of our operations, C and bar, with a collection of possible reductions of those strings. In other terms, the first part asks us to find the size of this set. the set of all words formed by C and bar such that CC can be reduced to the empty word and bar can be reduced to bar. So to start, let's just go ahead and start looking at finite words formed by C and bar. When we haven't done anything to a set, the finite word is just the empty word, that epsilon, and that corresponds to the identity operation, the one that doesn't change the set at all. In the length 1 case, nothing can be reduced because you'll just have C and bar. But once we get to the length 2 case, we start to see some cancellation, as bar is just bar and was already counted in the length 1 case, and CC is just the identity, which was already counted in the empty word case. For good measure, here is the length equals 3 case as well, where there are several cancellations that occur. The pattern to notice is that since any two adjacent C's or bars indicate that a string can be written as a smaller string, the only strings we are interested in are the alternating ones. So we get this list of operations. So we still have seemingly infinite possibilities for the number of different distinct operations you could make with closures and complements. So there are 2 different ways to approach this problem. One, benefiting from the fact that the solution to the problem is known and given in the problem statement as 14, you could just assume that the number of unique operations is 14, which would tell you that one of the operations in the length equals 7 case can be reduced to a smaller operation string, and then find an example to show that all 14 of the operations can be distinct for a set in a topological space. If you don't know that 14 is the target number, which is possible given that other books state it without giving you 14 for free, you could start picking examples of sets and see how many of these operations you could use to generate new sets before repeats occur, and then conjecture another reduction that is possible based on your computation. This would essentially be doing the second part of the problem as we've stated it first, and it'll probably be more clear if we go that route. So I'm going to go ahead and pause here if you want to think about how you would construct a set that would realize 14 different sets under closure and complement. The easiest place to think about this is probably where we're all most familiar, is the real numbers. So the idea would be to take some subset of real numbers where if you apply these different strings to them, you would get 14 distinct sets. So I'll give you a second to pause if you want to. Otherwise, I'm going to start talking about the example and how to construct one in general that would work. So we're going to go ahead and construct a set on the real line in the following way. First, go ahead and pick 2 open intervals that meet at a point but do not contain that point. For my example, I'm going to use the interval from -2 to 0, non-inclusive, and the interval from 0 to 1, not inclusive. Then second, pick some single value that is not one of the endpoints of those open intervals and is not contained in one of those open intervals. Lastly, and this is the main trick, take an interval intersected with the rational or irrational numbers. I'm going to go ahead and look at the open interval from 5 to 6 intersected with the rationals for my example. And you go ahead and take these 3 different things that you chose in these 3 steps and you union them together, and that will be your example. As you run through the operations, you'll end up getting these sets. The first important thing to notice is that there are 14 different sets realized and 2 places where the diagram loops back around. One at bar C, bar C, bar C, bar, which is length 7, and another at bar C, bar C, bar C, bar C, which is length 8, and contains bar C, bar C, bar C, bar. So the conjectured reduction is that bar C, bar C, bar C, bar is equal to bar C, bar. So just to state it one more time, we're going to go ahead and prove that bar C, bar C, bar C, bar is equal to bar C, bar. And we're going to do so using the notation of this less than or equal to relation that we developed earlier on in the video, along with just how the interior closure and complement operations manipulate that less than or equal to sign. So if you want to think about the proof, this would be a good place to stop, and I'll give you a second to do that. Otherwise, I'm going to go ahead and talk about the proof. So just as a refresher, the main tool involved is the less than or equal to idea that we defined earlier on these strings of operations of closures and complements, along with the containment properties of the interior, closure, and complement on this relation of less than or equal to. We should go ahead and summarize them again. So there are 5 things to remember about this less than or equal to relation. First off, if you have two operations, O1 less than or equal to O2, then the complement operation is going to switch that relationship. So the complement of O2 will then be less than or equal to the complement of O1. 2, if we go ahead and apply the interior to something, so C bar C O1 is always going to be less than or equal to the original operation O1 because the interior is always contained by the original set. 3, the closure and interior are isotomic operations. So if you have O1 less than or equal to O2, that implies that the interior O1 is less than or equal to the interior O2, and the closure O1 is less than or equal to the closure O2. 4, bar is going to be equal to bar because that's a reduction. And lastly, if O1 is less than or equal to O2 and O2 is less than or equal to O1, then O1 must be equal to O2 as operations. So let's go ahead and consider the operation C bar, C bar, C bar. This is the same as the interior operation C bar C applied to bar C bar. So we have that C bar C bar C bar is less than or equal to bar C bar. Then applying the closure to both sides, we yield bar C bar C bar C bar, which is the length 7 thing that we're interested in, is going to be less than or equal to bar C bar by the fact that closure is isotomic. But then the bar C bar operation can be reduced to bar C bar because bar is just equal to bar. Next, we're just going to consider the closure by itself, or bar. Then if we go ahead and apply the interior, we'll have C bar, which is less than or equal to bar. Further, since bar is idempotent and doesn't affect the sign, we have that bar C bar is less than or equal to bar, which equals bar. We can then go ahead and apply the complement to both sides, which will reverse the signs. So C bar is greater than or equal to C bar. And then lastly, applying the closure operation to both sides again, we yield that bar C bar is greater than or equal to bar C bar. So bar C bar is both greater than or equal to and less than or equal to bar C bar. So it must be the case that the two operations are equal, and thus you have a total of 14 possible distinct operations. And we already looked at a set that realizes different sets for each of the 14 possibly distinct operations. Thus, the maximum of 14 is achieved and is achieved on the real numbers. And so yeah, that's essentially one of the ways you can think about Kuratowski's 14 set theorem and how you could prove it. Now, mind you, it's a lot easier than being Kuratowski in the 1920s and thinking about it because we knew that 14 is the answer and we knew that this thing was true, right? We weren't sitting at a table like, I think this thing is true, I want to prove it, how do I do that? Which is usually where you are when you're thinking about new things in math. But anyway, that's essentially all I've got for you today. It was a cool problem to talk about because, 14 comes out of nowhere and it's a pretty cool thing that happens in topology and just a weird way that 2 times 7 or 14 comes up somewhere in math. There's another place that it comes up, but I don't have enough knowledge to talk about Banach spaces at this time. So yeah. That's pretty much it. If you enjoyed this video, give it a thumbs up and subscribe for more of the chalk stuff that I do here. I also talk about my PhD experience as well, which I will put up there if you're interested in how that's going. But yeah, as always, I am Nathan. This was chalk for once in a long while, and I will see you next time. Yes.